Hey guys, welcome to STEMBros, Green here. And what I have for you here today is Form 4 Physics Chapter 1 Measurements. Let's begin, shall we? Right. First of all, we'll be learning two parts here. 1.1, learn about the types of physical quantities, and 1.2, learn about the interpretation of graphs. Right. Let's start with 1.1 physical quantities. And you might be wondering, what is a physical quantity? Well, a physical quantity is a property that can be stated in its magnitude and unit. What does this mean? Let's look at some examples. Here we have a ruler. There's 1 inch, 2 inch, 3 inch. This ruler measures length. And the 1, 2, 3, 30 and stuff here represent its magnitude. And inch, meter, centimeter is its unit. Another example we have is the scale. This scale measures mass. This red ball weighs 1 kilogram. 1 is its magnitude, kg, kilogram is its unit. Now, we actually have two types of unit here, metric unit and imperial unit. Examples of it are liter, meter, and kilogram, while imperial unit is gallon, yard, and pound, which each representing one type of category. For our purposes here, we will be mainly focusing on the metric unit. Right, let's continue. There are actually two types of physical quantities, which are base quantity and derived quantity. Base quantity are physical quantities that cannot be derived from another physical quantity, or in other words, is the basis of other quantities, whereas derived quantity is physical quantity that can be derived from base quantity through multiplication, division, or both. Now, you may be wondering, what does this thing mean? Like, what does this derived mean? Or what do you mean by basis? Well, let's look at some examples. Alright, first of all, we have length, the ruler that I've shown you before. Can you further break down length into other quantities? I'll give you a while to think about it. Nope. Length is already the simplest quantity and is unable to be further broken down. Thus, length is a base quantity. Now, you may be thinking, what about derived quantity then? Here's another example. Speed. Can you further break down speed into other quantities? Again, I'll give you some time to think about it. Okay. Yep. According to the formula, speed is actually equal to distance over time. Thus, speed is a derived quantity. Now, let us have a look at the base quantities. First of all, length. Its symbol is represented by little l, and its SI unit is m, meter. Example here is the meter ruler. Next, mass. Symbol is represented by little m. Its SI unit is kilogram, kg, kilogram. This is a dumbbell representing 1 kilogram. Third one we have is time. It's represented by the symbol little t. Its SI unit is second, s. This is a stopwatch which represents the time. Next, thermodynamic temperature. Keep in mind the word thermodynamic is actually important. It's crucial to write it as thermodynamic temperature and not just temperature. It's represented by the symbol T, the big letter T, and its SI unit is Kelvin, K. This is a thermometer representing it. Next up we have is electric current. It's represented by the symbol capital I, and its SI unit is A, representing ampere. This is an ammeter, representing the electric current. Next up we have is luminous intensity. Its symbol is represented by LV, a big letter L and a small letter V. Its SI unit is candela, represented by CD, candela. And the final one we have is amount of substance, represented by the symbol little n. And its SI unit is mole, represented by MOL. And these are the basic units that you will be learning at this level. There are a total of 7 basic units. Now, you may be wondering, how many derived quantity are there then? Well, actually, it's theoretically infinite. Why? Since derived quantity is multiplication and division of base quantities with each other, there is technically no maximum amount of it. Let's look at some common examples. First up we have is area, represented by the symbol capital letter A. Area is the multiplication of two lengths, so it equals to L squared. Its SI unit representation is meter squared, m squared. Next, velocity, represented by the small letter v. V is the length over time, t. Is represented by the SI unit meter per second, ms to the power of -1. The third one we have here is acceleration, a. A is equal to velocity over time, or in other words, the length over the square of time. Its SI unit representation is meter per second, ms to the power of -2. Next, force, represented by F. F is equal to ma, or you can say it as F equals to m, which is mass, multiplied by length, L, and divided by the square of time, t. The SI unit representation is kilogram meter per second, kg ms to the power of -2, or Newton, N. There is a special SI unit for force, which is this one here, Newton. And last but not least, we have energy or work, represented by the symbol W. W is equal to force multiplied by length, or in other words, mass multiplied by length squared over time squared. The SI unit representation of it is kilogram meter squared per second, or kg squared s to the power of -2, or same as the force, it has a special SI unit known as joule, represented by a letter J. Right. There's actually another type of physical quantities that can be used here, which are vector quantity and scalar quantity. Vector quantity is physical quantity that has both magnitude and direction, whereas scalar quantity are physical quantities that has magnitude only and does not have direction. There are 5 vector quantities that you will be learning. Displacement S, velocity V, acceleration A, force F, and momentum, the little p. You may be wondering, what does this mean? Well, let me answer you with a simple and straightforward showing of what these two actually mean, the displacement and distance. They both are representation of length, but displacement is the length between the initial position and final position, whereas distance is the total length of the route traveled. Let me show you an example. Here, you are standing here. You travel 30 meters to the right and 40 meters upwards. The total distance between your initial position and your final position, according to the Pythagoras theorem, is 50 meters. Your distance traveled is 30 meters plus 40 meters, which is 70 meters, whereas your displacement is the 50 meter here. This also shows that displacement has a direction, whereas distance does not have direction. If you are unclear about that, let me show you another example. Let's say you walk back to your initial position according to this rule. So your distance traveled would be 30 meter plus 40 meter plus 30 meter and plus another 40 meter, which is equal to 140 meters. However, your total displacement is 0. Why? Because you are at your initial position. Your length between the initial position and the final position is 0. Thus, the displacement is equal to 0. I hope you can understand my explanation. Hooray! You have successfully passed the 1.1 physical quantities. Now, let's move on to 1.2 scientific investigations. Look at this graph. You may be wondering, help! I don't know how graphs work. Don't worry, my friend. We will walk you through the graphs. First of all, what we have here is directly proportional graph. This graph is special because it's a straight line that passes through the origin, which is the 0, 0 point here. And how do we interpret it? We will say that y is directly proportional to x. Next up, we have linearly increasing graph. It's different from the directly proportional graph because it is a straight line that has positive gradient but does not pass the origin 0, 0, evidenced by here. How do we interpret it? We say it that y increases linearly with x. Now, you may be asking, what is linearly? Well, linearly means that when the x value changes, y value changes by a constant amount. For example, when y equals to x plus 1, every time x increases by 1, y also increases by 1. However, do note that this explanation isn't accurate, but is enough for now. Let's move on. The third one we have is linearly decreasing graph. Why is it special? Because it's a straight line that has negative gradient but does not pass through the origin, which means that it is moving downwards. How do we interpret it? We will say that y decreases linearly with x. Alright, next one, we have increasing graphs. They look like this. Their characteristics are they are a curve that has positive gradient that passes through the origin. How do we interpret it? We'll just say that y increases with x. Simple, isn't it? And next up, I guess you have already known it, decreasing graph, where it decreases. It's a curve that has negative gradient that does not pass through the origin, which is 0, 0. How do we interpret it? Well, we say that y decreases with x. Yep, this is just that. It's very simple to interpret it. And now we are approaching to the hard one, which is inversely proportional graph. From you can see here, it's a curve. However, from here, it's become a straight line. Now, why is it like that? Well, its characteristics are a curve that has negative gradient that does not touch the y-axis and x-axis, evident by here. Or it's a straight line that is directly proportional when the x-axis is 1 over x. This is very important. It's not the usual x you see here. It is 1 over x, which is the inverse of x. Well, how do we interpret this graph then? Well, we will say that y is inversely proportional to x. And congratulations, that is all the types of graph that you will be learning for now. And now you may be wondering, how do I analyze the graphs? You say that this graph is like this and like that, but you never told us how to analyze it. Well, don't worry, I haven't forgot about that. Alright, the first one we have here is relationship, which is the relationship between the variables. By looking at this graph, we'll say that y increases linearly with x. Next, gradient, the incline of the line. By looking here, we have 2 points, 2, 2, and 10, 6. By using the gradient formula y2 minus y1 over x2 minus x1, we will get that its gradient is 1 over 2. Area, which is the area under the graph. Area is equal to the area of this triangle plus the area of this rectangle. Or you could also say that it's the area of this trapezium. For our purposes here, it's equal to the 1/2 of 10 minus 2 multiplied by the 6 minus 2 plus the area of this rectangle here. 10 minus 2 multiplied by 2 minus 0, which is equal to 32 units square. The fourth one we have is interpolation, which is to determine the value at a certain point. If x is given, then draw lines to determine y at that point and vice versa. What we have here, when x is equal to 4, we draw a line at x equal to 4. When it touches the graph, we will draw a line to the y-axis to determine its position, which for our example here is equal to 3. So y is equal to 3. And last but not least, we have extrapolation, which is to determine the value of an unknown point. What we did is we extended the line or graph to find the y or x value of a point. For our example here, if we want to find the value of x when y is equal to 7, we will extend the graph by drawing dotted lines. Then at y is equal to 7, draw a dotted line towards the graph. When it touches the extended graph, we draw a line to the x-axis to indicate its position, which for our case here is x equal to 12. So when y is equal to 7, x is equal to 12. And that's all! Hooray! Give a big round of applause to yourself. I hope you enjoyed today's video, and I hope to see you in the next video. This is STEMBros and I'm Green, and thank you for watching.